Okay. So welcome everyone to the problem solving tutorials for 2024 and a quick intro. So Nicole and I aren't your instructors, but we're here today just to say hi, and I'll also be proctoring this session. Below we have all the contact details. If you want to reach any one of us, you can do that. The top three are mainly for like admin stuff. If you have any queries about what we do and stuff like that. The bottom two are the emails of your instructors. So if you have any content related questions, you can feel free to reach out to them by email. And okay, so we're just gonna go through some basic rules. So try to avoid interrupting the instructor when they're speaking. If you have a question, you can use the hand up reaction button or you could like send a message in the chat that you have a question and your instructor will address you as soon as possible. Also, there will be opportunities for you guys to engage in discussion. So please do unmute yourself then and share your thoughts because we want to keep this as interactive as possible and we want to hear your ideas. Also, please do not be disrespectful towards others or just use inappropriate language. We also strongly encourage students to have their cameras on as it makes classes more interactive, seeing each other's faces. And also, could you please change your usernames on Zoom to your full real name, just so we can keep track of who's here and we know yeah. Okay, some technical stuff. So the proctors will be in each session for, I guess, technical issues. So you can just direct message your proctor and we'll try to help you solve these issues as quickly as possible. Also, please be aware that we are recording each lesson. So if you feel uncomfortable with us videoing anything, let us know and we'll try to keep you out of it as best as possible. And also we will be sending out weekly reminders about when class times are and try to make as many of these classes as you can, especially since that we cover different content every session. So it's good to come as often as you can. Okay. So in case you do want to find course content after class, we have that on our website and we also will post video recordings of classes onto YouTube, so you can also check it out there. We also use a Discord server, which we highly suggest you to join if you do use Discord. It's a great platform where you could ask questions, even if they're not related to the course content, like as long as they're math related, we can try to help you answer them. But other than that, that is all from me, and we'll start with the instructing stuff from your instructors. I'll pass it on to them.
Hello, hello, hello. Okay, can everyone see the PowerPoint? Alright, this week we're doing number theory with me and Jay. This is our self-introductions. I enjoy maths and I like teaching maths. And I would like to invite Jay to read his introduction.
Okay, so hi, my name's Jay. So I'll read my introduction in case you guys don't want to read it. So in my spare time, I like going to the library. I think it's like a pretty cool place. You can like get books and stuff. My favorite book is Euclidean Geometry in Maths Olympiad. And then another thing that I'm interested in besides math is debating. Like I'm not that good at it, which is a bit sad. So then there are some like other facts. Those are my two favorite numbers. So yeah, it's pretty cool. Oh, okay.
That was quite interesting. Thank you, Jay. Today, we'll go over divisibility, the division algorithm, and modular notation, and primes. Okay, so firstly, we're going over divisibility. The definition of divisible is if a number b divides a number a, then there is an integer such that, I mean, no, if A divides B, then there's an integer such that, okay guys, we're starting. If A is a multiple of, okay, understand divisibility, we'll first go over multiples. And like, for example, the multiples of 5 are 5, 10, 15, 20, and so on. More formally, a multiple of A is an integer times A. Yep. And now we move on to divisibility. So a number E divides a number A if A is a multiple of B. So that means A is B times an integer, or A over B is an integer. And the symbol for divisibility is a vertical line. Yep. So now we'll go over some basic properties of divisibility. The first one is for any integer x, x divides x. And to prove this, I'll pull out my favorite writing software. Yeah, but we're proving that x divides x, which is the same as there exists an integer, which is the same as x over x is an integer. How do we prove this? We prove this by showing that x over x is 1, which is an integer. That's the first property. For example, 5 divides 5 and 10 divides 10. It's pretty cool. Okay, the second property is that 1 divides x for any integer. It's the same as x over 1 is an integer. X over 1 is equal to x, which is an integer. Now we'll move on to some more properties, which I'll let you guys have time to prove now. I'll give 5 minutes. By the way, an integer is a whole number, like 5, negative 10, and 0, all integers. By the way, we're proving that these properties on the slide are true, each of them. So x divides 0 if x divides y and y divides x, and x divides and y divides z, then x divides z, and so on. Okay, so hopefully that's enough time to try the problems. And now I'll prove them. So again, for the first one, x divides x because x over x equals 1, which is an integer, and x 1 divides x because x over 1 equals x. It's integer. And x divides 0 because 0 over x equals 0, which is an integer. And now the next one is a bit more challenging. So we know x divides y, so y over x is an integer, and y divides z, so z over y is an integer. And we want to prove x divides z, which is the same as z over x is an integer. And z over x is equal to z over y times y over x, which is integer times integer, which is an integer. So therefore, x divides z. The next one is even more challenging. We'll do that one last actually. So the next one, so skipping that, if x divides y, then x divides yz. X divides yz is the same as yz over x is an integer. And we know yz over x is equal to z times y over x, which equals integer times integer, which is again an integer. Someone asked, why do you swap the fraction digits around? Oh, do you mean for the notation of this? Okay. So we have like, for example, 6 over 3 is 2. But we also say 3 divides 6. That's just notation. You can think of the symbol meaning divides. So 3 divides 6. Whereas in this example, it is this symbol, the slash, not the vertical bar, means divided by. So 6 divided by 3. Yep. Next one. If x divides y and x divides z, then x divides y plus z. So x divides y, which means y over x is an integer, which means y is equal to integer times x. And x divides z, which means z is equal to another integer times x. So z plus y is equal to integer times x plus integer times x. Integer 1, integer 2, which is equal to x times integer 1 plus integer 2. And second to last, or the last one in that screenshot, if x divides y and x divides z, then x divides ay plus bz. This is very similar because y is equal to an integer times x. So ay is equal to a times integer times x, and z is equal to b times integer times x. So bz. So ay plus so ay plus bz equal to a times integer plus b times the other integer times x, which is an integer times x. And now finally, if x divides y and y is not 0, then the absolute value of y is greater than or equal to the absolute value of x. I don't know why it's on the next slide. Sorry if anyone didn't see that. Firstly, to make sure everyone understands, the absolute value is the positive of the number, right? So we have some examples. Yep, so you just remove the negative sign. And also, we specified that y is not 0 because x divides 0 for any x. Then, yeah. So if x divides y, then y is equal to some integer times x. And we know the integer is not 0 because otherwise y is 0. So for example, the integer can equal 1, 2, 3, 4, 5, and so on, or it can be negative 1, negative 2, negative 3, negative 4. you get 5. And so on. So y is equal to, for example, x, 2x, 3x, 4x, and so on, or negative x, negative 2x, negative 3x, and so on. And all of these, the absolute value of any of these is greater than or equal to the absolute value of x. Yeah. So now we'll move on to some problems, which you guys will have some time to do. We'll give 3 minutes and then we'll present the solution to the first one. And yeah, you get more time for the other ones. You can do the next ones if you finish early. Oh, okay. In problem 3, there's a typo. Instead of for 2 all integers, it means for all 2 integers, x and y. We'll start on presenting the solution for problem 1, which will be presented by Jay Zhao. It's very cool.
Okay, so I'm gonna like quickly share my screen. Oh, okay. Unfortunately, I
Oh,
can't
I'll
share my
share.
screen. Wait, what? Oh,
Wait,
dang.
can you still share if I share?
Oh yeah, I can. Right. Oh wait. Can you guys see my screen?
Yes.
Okay, that's good. So, okay. So can someone like, wait, Houghton, can you just like say what the question was like out loud?
Wait, show that if n bigger than 1 is an integer, then we can't have n divides 2n squared plus 3n plus 1.
Okay, so the first thing that we can see is that like, using the properties that we've found before, you can see that n divides like 2n squared plus 3n, because we can write this as 2n plus 3. And then we can also see that because n is greater than 1, n does not divide 1. So then, what we have here essentially is that like n divides a, and then and then n doesn't divide b, and then we want to prove that n doesn't divide a plus b. So if we assume that like n does indeed divide a plus, wait. Okay, so like I think like this is like a good like lemma for you guys to think about. So like, because this is like also a property that's like very useful for like the other questions. So just think about just quickly think about like what approaches you might have like in trying to prove this.
能走了。下题就不知道在纸上是什么。
捞给你买，然后从电脑里边从laptop 里边出来。今天你
Okay, well, it's just like, so here, like, what we can do is, if we see that, like, if we assume n divides a plus b and n divides a, then we can get that n divides like, a plus b minus a, which is like one of the things that we've proven before. And this tells us that n divides b. However, like before, our assumption is that n doesn't divide b. So this leads to a contradiction. So therefore, n doesn't divide a plus b. So like, you can like if you look at this is like really helpful for the next question as well. Yo, okay, I'll stop screen sharing. Oh wait. Oh yeah, those are like also like valid ways to do this question. Alistair just asked like what A and B are in this question. So what we've done is like, the question asks us to prove that n doesn't divide this, and this is like made up of two parts. We can let this be A, and let this be B, and so n divides A and n doesn't divide B. Yeah, and then some people like they have like another way of doing this question, which is also correct. So I'll just like quickly talk about this. So so like what you can also do is you can have like this, and if you show that this is like not an integer, it proves that if you can show this is not an integer, it also like proves that it's not like divisible. And then as some people have done, this is like equal to 2n plus 3 plus 1 over n. And since this bit's an integer and this bit's like not an integer, the whole thing's like not an integer. Okay, does that make sense to everyone? Okay, I'm gonna assume it makes sense. If no one like says anything. But...
We'll give another minute for this problem. Okay. Would Izal like to present his solution for problem 2?
Okay, wait. Yeah, sure. Okay, I'm just gonna screen share again. Which I can't right now because I was in the
Okay,
screen
wait,
sharing.
screen share,
Yeah.
screen share.
Right.
Oh, oh yeah, would anyone else like to present their solution?
Okay, I'm gonna like count to 5, and if no one volunteers, I'm gonna present my solution. Okay, 5, 4, 3, 2, 1. Okay, guys, I'm gonna present my solution now. Okay. So, okay, Houghton, could you please read the question out to me again?
If A is bigger than B, show that we can't have A divides 2A plus B.
Okay, so this is like what the question is saying, right? And then once again, we can split this up into 2 parts, which is like we can see that A does divide 2A because like 2A over A is equal to 2, which is an integer. It's also like a property we've proven before. And then another property we've proven before is that if A is greater than B, or like if they're both positive integers, then A can't divide B. Okay, so this like makes sense, right? So then what we've like something we've shown before is that like if we have like I'll just use different numbers here. So like if we have like n divides m, and okay, wait, what's another letter? I'll just put okay,
B.
and m doesn't divide like divide k, then this tells us that n doesn't divide m plus k. And so this is like the lemma that we had before essentially. So if we use this lemma on these like 2 things we've proven, we can get that like a does divide 2a does not divide 2a plus b. And then that's true. Okay, so like does that like make sense to you guys? Okay, so then okay, I'm gonna assume that like all made sense. And then like I'm just gonna talk about what Alistair said again. So like something you can also wait, yes, that is quite good thinking. So like something you can also do, as Alistair said, is just like you can divide. Oh, it's like okay, like if you guys are, I'll just like explain what Alistair did. So like the multiples of A are like like 1A, 2A. I'm not like this isn't really a formal proof. I'm just like so like the multiples of A are like these, right? And then because B is like less than A, like the number 2A plus B is somewhere in here, but then it's like not either of these. So then it's like not a multiple of A. That's like essentially what Alice's like what Alice's way of doing it is, and that like it's yeah, it also like does work. So yeah, that's quite good. And then I guess like you guys can go back and look at the 3rd question.
Okay, we'll give you guys another minute. Someone made a very smart observation. He said n should be non-negative, and that's because negative powers, yeah, it's just not true anymore. And you know, n has to be positive. Oh no, non-negative, non-negative. Guys, mine NZ made a very good question. I think you should ponder it. Okay, would Jay Zhao like to present his solution for problem 3?
Okay, so like I'll ask this again. Like, does anyone want to present their solution? This time I'm gonna count down from 10. So 10, 10, 9, 8, 7, 6, 5, 4. Oh, like if you don't have any idea how to do this problem, it's fine because this problem is like I think it's pretty tricky. And then like you do need to have a bit of like other knowledge to solve it. So like yeah, it's fine. Okay, I'll continue counting. 5, 4, 3, 2, 1. Okay, so I'll do my presents. I'll go present because no one else wanted to present. Okay, so okay, I'm assuming you guys can see my screen. Okay, so before we like, I'm just gonna like try some small cases and like see like what we can get here. So when we have x minus what the x minus y divides this is n equals 1. So yeah, this is true, right? Oh wait, I forgot when n equals 0. I'll do n equals 0 first. So it's just what the heck 0 and then oh 1 minus 1. So x minus y divides 0, and then this is like always true, right? And then when n equals 1, we have y minus 1. Oh, x minus y divides x minus y. And then this is also true. That's good. And then like these are kind of like the very easy cases. So let's try like some bigger numbers. When we have n equals 2, we want to prove this, right? And this is kind of tricky, but then like very like so can anyone think of like something like clever that we can do to like involves like these terms? Just like just type in like chat if you like have any ideas like for what to do in this case. Yes, Frank, that's correct. So what we can notice is that like these two things are actually the same. So then if we like divide x minus y squared by x minus, like if we do this, then we get x plus y, right? Does this make sense to you guys? And then x plus y is like an integer, so then we've proven that it's divisible. Okay, does that make sense? you can type like yes in chat if it makes sense, or like no if it doesn't make sense. Oh yeah, that's great. That's great. Like it helps like if you guys say like if something makes sense, because like I don't have to worry about like if I'm explaining it enough. So let's try n equals 3, right? So then x minus y divides x3. See, and then like okay, so I'm just gonna like tell you guys like something you can do here is that notice that x squared minus y squared is equal to x squared plus xy plus y squared. And then like by doing something like similar to what we did before, we can get that like it's divisible. So then like if you guys like don't already know this, like for any xn minus yn, we can always factorize it to be like this. I'll just write it out. Oh, it's a bit annoying to write out, but it's x n minus 1 plus x n minus 2y plus x n minus 3y squared, and then plus dot 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 plus y n minus 1. Right? And then so what this means is that since like there's always this x minus y term here, we can always divide it by x minus y, and then we get this bit, which is always in we always get like this bit left over, which is an integer. So that tells us it's always divisible. Okay, so Jimmy, like you probably can do it with induction, but like yeah, you probably can do it with induction. But like I think this like it would have been okay. Do you guys want me to prove that this factorization always works? Okay, I'll just like yeah, okay, Jimmy, would you like to like like oh okay, I'll just like go back a bit. So like something we notice is that like this we is equal to this, and then this is equal to this. So that kind of motivates us to like think that we can always write like a difference of difference of powers. Like we can always factorize it with like a x minus y term in front. Like yeah, this is like a bit hard, I guess. So like if you guys want me to explain it more, that'll be fine. Okay. Okay, yes, Chris, I will do that for you. So for the case when n equals 5, this is equal to x minus y x4 plus x3y plus x wait, is that right? Yeah. Plus xy plus y4. And then if we actually go out and expand this ourselves, we see that this is like actually true. So I just want to quickly make sure that this makes sense, like that makes sense, and then I'll go about like proving it if you guys want me to. Also for like, I'll just quickly expand. Okay, I don't think like the proof for this is like a bit tricky, especially if you don't already know the content. So I guess I'll just do this example. I'll just expand it. So when we expand it, we first like do this bit. So it's x5 plus x4y plus x squared y x cubed y squared plus x squared y plus y4. And then when we multiply by y, we get like minus y x4. Oh, I'll put it on the side. Minus x y. Huh? Oh, thank you, Chris. That's a very good observation. Thank you. Thank you. And then, so, okay, this is what we get after we finish expanding it all. And what's pretty cool is that these terms cancel because we have like plus this and minus this, so they cancel. And then these cancel, then these cancel, and then these cancel. So at the end, oh, this should be a 5, by the way. So then at the end, we get x5 minus y5. So we've proved, like, no, we haven't proven, but we've shown that the right-hand side is equal to the left-hand side. So this is just an example of how this factorization works. When n equals 5. Like, it's fine if this is like a bit confusing, I guess, because like this is a pretty tricky like thing. And then what's pretty cool is that we can also do a similar thing for like for other ends at the top. But like I feel like it's like a bit cumbersome to like write out. So I hope you guys like can like kind of see what the idea is here. So just like say yes if like this like sort of makes sense. Okay, yeah, sorry guys for like yapping for so long, but yeah, I just wanted to make sure you guys like all understood. Okay, now back to how to.
And that was very educational. Thank you, Jay Zhao. Anyways, there was a very popular question during that problem, and it was whether 0 divides 0. Okay, firstly, if you look at the properties, we actually prove that x divides 0 for any x. So therefore 0 divides 0. Okay, but the problem that people are having is that okay, the way I did this was a divides b if b over a is an integer. This was actually wrong. It was incorrect. I'm very sorry for that. I thought it would make it more intuitive, but I made it incorrect. The proper definition for a divides b. Well, I'll make a new paint. I don't know how to remove this. Okay, but anyways, if you guys recall, definition for divisibility that I taught you was a divides b. A divides b if and only if b over a equals k, or some integer k. This is actually incorrect. The proper definition, a divides b, is a is equal to b times k, for some integer k. These two do look very similar, right? If you if b is equal to a times k, right? If you multiply both sides by a, then you get this. However, this is the correct definition, right? And you can't get from this to this. Why is that? It's because we can't divide by 0, right? If a equals 0, then b over a is not k. Because we can't just divide both sides by a, which is 0. So, I mean, for every other a, this definition and this definition are the exact same, by the way, because then you can divide by a. If a, now we want to know if 0 divides 0, which is the same as, does there exist an integer k such that 0 equals k times 0? Yeah, there's quite a lot of integers k. For example, 0 is equal to 1 times 0, equal to 69 times 0. It's also equal to -5 times 0. There are many options for k, and any of these do prove that 0 divides 0. Okay, so now we will move on to the next slide. Does that make sense for everyone, by the way? Okay. So now we'll move on to the division algorithm. So here are some examples of the normal division you would do. 30 divided by 6 is 5, and the remainder is 0. So then we can also rewrite this, right? We can write 30 is equal to 5 times 6 plus 0. Then there are more examples for 25 over 4 with remainder 1, 29 over 15 with remainder 14, and 7 over 8 with remainder 7. And then notice how we've rewritten these divisions into multiplications. Division algorithm is just rewriting it like this, right? So for any A and B, there exists Q and R such that B is equal to Q times A plus R, where R is between 0 and A. So for example, in 30 divided by 6, Q would be 5 and R would be 0. And in 29 over 15, Q is 1 and R is 14, which is less than A, which is 15. As you can see, under that, I have rewritten it in the division form. The important part of this is that there exists unique integers Q and R. For example, in 30 divided by 6 is equal to, this is the same as 30 equals to 5 times 6 plus 0. There are no other options for Q and R. It has to be 5 and 0. I'll give you a moment to ponder this thought. Oh, the big R, that was just my way of writing the remainder. Someone asked what the R means in the first 4 examples. So like 25 over 4 is equal to 6 plus 1 over 4 because there's a remainder of 1. So that's why it's R1. I'll give 1 more minute to ponder the division algorithm. I'll present an explanation. So we want to prove that there exists unique Q and R such that A is equal to Q times plus R. So for example, 30 over 6 is equal to 5 times 6 plus 0. This is Q and this is R. Suppose we found a different Q. Maybe this time Q is equal to 4. So it's 4 times 6 plus some other R. But this means, okay, wait, 30. This would mean 30 is equal to 24 plus R. So that means R is equal to 6. But we specified that R is between 0 and A. And in this case, and B. And in this case, B is 6. So this doesn't work. It's because if you change Q by even just 1, then we're adding a whole another B. And the size of the range that R can be in is B. So intuitively, if you add or subtract multiple B's, then R will have to change by multiple B's. And so it will definitely exit this range. Does everyone kind of understand what's happening? Someone asked what the difference is between the uppercase and lowercase r's. Yeah, this was a bit confusing for many people. I'm very sorry for the way I wrote this. Okay, so the question is about these r's at the top and the r at the bottom. Yeah, so 30 over 6 is equal to 5r0. That's the remainder, right? Because 30 divided by 6 is equal to 5, and 6 fully divides 30. However, in the next example, 25 over 4 is equal to 6 plus 1. If we divide 4 into 25, that's equal to 6.25, or 6 plus a quarter. This is where that comes from. I don't think this is proper notation, by the way. Actually, maybe it is. But I don't think there's proper notation. Okay, but like, you know, when you do your long division, and then you have that remaining number. Yeah, that's the number after. That's the second number. And then in the second part of the slide, for all integers a and b, there exists unique q and r. That r is just a variable, and it is the remainder. So yeah, they would actually be the same number, right? 30 over 6 is equal to 5 r0. Same as 30 is equal to 5 times 6 plus 0. 25 over 4 is equal to 6 r1 is the same. That's 25 is equal to 6 times 4 plus 1. All right. This is q, and yeah. You can rewrite that, or you can change the r here to a big R. So now we will move on to the next slide. Okay, modular notation. This is just another way of writing stuff. And there's no new maths yet. So if we read this, modular relates closely to divisibility. However, in mod, instead of focusing on both the quotient and remainder, we only care about the remainder. Yeah, so the way we use modular note, okay, well, I'll let you guys read the slide. Yeah, hopefully that's enough. Fine. So, yep, A is okay. It's meant to be a triple line equal. Oh, actually, I have an idea. I'm a super genius, guys. Okay, anyways, A is congruent to R. Why'd my font? Okay, the font changed. A is congruent to R mod B, where R is the remainder of A when divided by B. Yep, so this R is the exact same as the R in the division algorithm, but we just don't care about the Q anymore. For example, 9 is this is read as, okay, this is read as A is congruent to R mod B. So for example, what is 9 mod 6? It would be okay. Some people are confused by the triple line equal. Again, it's just notation. It was just decided that you write this modulus thing, using a triple line equal. Yeah, there's nothing else about it. So what is 9 mod 6? It's congruent to 3, because 9 divided by 6 is equal to 1, with remainder 3. What is 6 mod 15? Congruent to 6. What is 15 mod 5? Oh yeah, it's congruent to 0. Because, okay, in each of these cases, 6 over 15 is equal to 0, 6. And 15 over 5 is equal to 3, 0. So 0, 0, 6, 6, 3, 3. Yep. So does everyone understand that? I will count down from 5, 5, 4, 3, 2, 1. Okay, I think that means everyone understood it. Okay, so now we have some problems. You guys have 30 seconds to do, actually 1 minute. Yeah, you guys have 30 seconds to do this. And then Jay Zhao will kindly present the solutions. Does anyone know what time the lesson is meant to end? Okay, thank you, thank you. Hopefully that was enough time to do these problems. 16 mod 4. 16 is divisible by 4, so the remainder is 0. So, okay. You guys have 10 more seconds to do this. Yeah. So those are the problems. 16 mod 4. What remainder does 16 have when divided by 4? It's 0. So therefore 16 is, oh no, I lost my triple sign. Is congruent to 0 mod 4. 27 over 12 is equal to 2, remainder 5, 3. So 27 is congruent to 3 mod 12. This isn't proper notation, by the way. Don't learn from this. But it's a triple equal. Actually, I'm so funny, by the way. Oh yeah, 237 divided by 14 is equal to 14, 17. No, it's equal to no, 16. 196, 224. 13, I think. If it's wrong, please tell me. Therefore, 237 is congruent to 13 mod 14. Oh, okay, wait. Would anyone like to answer these questions? Maybe someone thought of a unique solution. Yeah, I'll count down from 5. 5, 4, 3, 2, 1. Okay, I'll take that as a no. Okay, moving on. Oh, okay. Oh, okay. Next, we have primes. This is the definition of a prime. So yeah. Can people ponder why 1 is not a prime for a moment? Okay, by definition, a number is a prime if it has 2 factors. 1 has 1 factor. Yeah, that's why. Oh, okay, good job to Ala. She solved it. Would she like to present her solution? Okay, I think that's a no. Okay. Oh, no way, I stole a problem. I'm so sorry. Okay, can everyone try these problems for a bit? Except the first one. Unless if you didn't listen to me, we should be a bit rude. I'm very sad now. By the way, these solutions will be kindly presented by Jay Zhao. You guys have 1 minute for the second problem. Okay, could Jay Zhao please present a solution?
Yes, I will. Okay. Wait, let me find the questions real quick.
By the way, does anyone have any ideas that they would like to present? Okay, Jenny, you are. Yeah, nothing.
Okay, so
Nothing.
like, does anyone like, can anyone like just say what like all the even primes they think like there are? Okay, so everyone said 2. This is really good. Because yes, that is the right answer. And then, does anyone like have a reason to like why 2 is the only prime? The only even prime. Sorry. Uh, yes, that's true. Every even number. Also, every even number is divisible by 2. That's kind of like the definition of an even number, right? So then, okay, so then like with 2, when like you, okay, so this isn't like like with 2, when you divide it by 2, it's just like 1, right? But then with any other like even number, like just like with any other even number, when you divide it by 2, you get like n. And so like since n is not 1, it will have like at least one other prime divisor, right? Does that make sense? So then in total it has like more than like 2. Wait, what am I saying? No, it's like, okay, so with any other number, when you divide 2n by 2, you get n. So if n is not 1, then it's not prime, just like by the definition, right? Does that make sense, guys? Okay, one person said, or 2 people said yes. That's very good. 3 people, that's a lot of people. Alright, so then, let's just move on to the next problem then. Actually, I'm gonna do the last problem first because I like it more. So we have P is a
Wait, can we
prime.
give them a bit more time?
Oh wait, have you guys? Oh, okay, it's fine. I'll do problem 2 first. Then wait, do you guys need more time to do problem 2, or should I present?
I will count down from 5, 5, 4, 3, 2, 1. Okay.
Wait, when you say present, does that mean you want to present, or do you like want me to present? Okay. Yeah. Wow, that's so sad. No one wants to present today. Okay, so um, final positive integers, and where these are all, where all of these are prime numbers, right? Um, okay, so like I'm just gonna ask if like anyone has any ideas of like what we can do here. n equals 2. I think when n equals 2, okay, so let's just try n equals 2 because that's like a good suggestion. So this becomes 6 minus 4, which is 2. This becomes 8 minus 5, which is 3. This one becomes what does that become? Wait, what's 2? Oh, it's 10. Oh, and then 7. So that works. That's quite good. So then like, yeah. I guess like, does anyone like, because okay, we're gonna assume that these are the only solutions, right? So like, does anyone have any idea like why like there can't be any other solutions? Okay, well, no one has said anything, so let's just like make some observations here, right? I'm not sure exactly what that means. Okay, so Hao Tian has like he suggested, or he hasn't, you can't see this, but Hao Tian has suggested that we try some small cases, which like I think that's a really good idea. Thank you, Hao Tian. So
You're welcome.
when n equals 1, we have 3 minus 4, which is like minus 1, right? That's not like that's like less than like 0. It's not a prime, right? So then let's try n equals 2. Okay, n equals 2, we've seen like it works, right? So now n equals 1. Okay, n equals 3. When n equals 2, we have 9 minus 4 equals 5. 12 minus 5 equals 7. And then 5, yeah, 15 minus 3 is equal to oh yeah, it's equal to 12. And 12 doesn't work, right? Okay, so Alistair has, he said okay, so Alistair's made like quite a good observation, I think. And that is like, if we look at just equation 3, 5n minus 3, right? Like if n is an odd, if n is odd, then 5n minus 3, like this one's like, this is gonna be odd and this is also gonna be odd. So odd number minus odd number is an even number. And then the only even number that's a prime is 2. So that must be when n equals 1. Have we already shown that n equals 1 is in the solution? So that means that n is going to be even. So we can write n equals 2k because it's an even number. Wait, how do I copy this? Oh, it's okay. It's okay. So then, wait, Hao Tian, can you read out the problem to me?
Find all positive integers n for which 3n minus 4, 4n minus 5, and 5n minus 3 are all primes.
Yeah. Okay, so if we put this in now, we get 6k minus 4, 8k minus 5, 10k minus 3. This. Okay, wait. Hao Tian is like,
Oh, I was pasting the problems.
oh, that's so kind of you.
Yeah, I'm very kind.
Okay, so like what do you guys notice like here? Because we've shown that like okay, so Okay, just like okay, I want to direct you guys to like look at this one. What the hell? Okay, that was meant to be an eye, but it looks really bad. Okay, so like if we look at this top one, like what do we notice about it? Okay, it would be really cool if someone said something in chat, but like I'll count down from 5 again, and if no one says anything, I'll like yes, that's very clever. Yes. So this one's even, right? And then we know the only even number is the only even prime number is 2. So that means that 6k minus 4 has to be equal to 2. And then this, if we just solve for this, we get 6k is equal to 6, k is equal to k is equal to 1. So then that's the only possible value that works, right? And then we know that n is equal to 2k because like that's what we said over here. So now n is equal to 2 times 1, which is equal to 2. And so we've shown that this is the only solution, and that's like also the solution that we found here. Yes, mind NZ. That's very true. Thank you for explaining. Yes. So like can you guys just say yes in chat if like that all made sense? Okay, that's very good, very good. So I'll let Hao Tian start. Oh wait, no. Oh, there was another question, which is like, okay, so I'm just gonna assume you guys had enough time to try the last problem. So I'll just quickly do this. So P is a prime and P plus 2 is a prime, or like Q, but yeah. So P and P plus 2 are both primes. And then show that P plus Q has 3 prime factors, not necessarily distinct. Okay, so we're not really okay. I'm not gonna worry about the not necessarily distinct part. I'll explain it like if it comes up. Okay, so what we know is that these are both odd. So when you add 2 odd numbers together, you get like an even number, right? So that means that P plus Q has to be even, which means 2 divides P plus Q. So that's one of our prime factors. We found 1 prime factor. So now we have to find 2. So now I have to find 2. So that's good. Now, what we can also notice, let's just like, I think like, okay, so does anyone have any ideas of like where we can find this other prime factor from? Oh, that is a very good idea. We should do that. So 2 P plus Q is equal to P plus 2 is equal to 2P plus 2. And then this is equal to 2P plus 1. Does that mean we can't use 2 and 3? I think with the question, or Alistair, I think like with this question, like we want to find like, so an example of like a prime, like 2 primes, which are different by 2 is like 3 and 5, and also like 5 and 7. And then like we're only considering the cases where they're both like odd. So I hope that like makes sense. Okay, anyways. As Mind NZ has suggested, if we rewrite like P plus Q in terms of P, we have this, right? And then we have 1 prime factor here. And so like, let's just think about the P plus 1 term. What do we know about P plus 1? Remember that P was a prime. Yeah, Frank, that is true. But then like I'm just doing like another. I can talk about that later. But like, yeah. As Ethan has said, like P plus 1 is not a prime. Right, that makes sense, right? But like, okay, how do we know that p plus 1 is not a prime? Remember that p is an odd number, right? So then p plus 1 has to be even. So then that means that p has to be like, that means p plus 1 has to be like a number that's like 2 times like another number. So then k, since it's like if it's not 1, it has to have at least one other number dividing it. So if you look at it, here's one prime divisor, here's like another prime divisor, and here's the part where they say like not necessarily this thing. Like they're the same, but like we're counting them twice because they're like we're counting them twice, even though they're the same. And then since if k is not 1, then there's another prime divisor, right? So then overall there's like at least 3 prime factors, right? Does that make sense? I think that was like that was a bit confusing, I guess. But like, does that make sense? Say yes if that made sense. Oh, that's good. Okay, and then I think someone else someone else said this. So I'll just quickly go over this. So with p and p plus 2, we know that 2 divides p plus q because they're both odd, right? And then if p is not 3, then like 3 can't divide p and 3 can't divide q, right? Because the smallest prime, which is a multiple of 3, is 3. But since like none of them are 3, they like 3 can't divide them. And then we can notice if either p is 1 mod 3 or 2 mod 3, and then in those cases q, and then like if p is 1 mod 3, then q is going to be 1 plus 2 mod 3, which is like which means it's divisible by 3, so that's not possible. So then it has to be the case where p is 2 mod 3, and then in that case like q is 1 mod 3. Does that make sense? I think someone else has said this before. But then when you add them up, p plus q is equal to 2 is equivalent to 2 plus 1 mod 3. And this means that it's equivalent to 0 mod 3, which means that p plus q is also divisible by 3. So 2 divides this and 3 divides this, right? This is like this is when we're assuming that p is not 3. But for when p is not 3, we can just consider that manually. So like p is 3, then q is 5, and then p plus q is equal to 8. So then it's 2 times 2 times 2. And then so since p plus q is like divisible by 6, since when p is like more than 3, you have like something more than 3 plus something more than 3, and then so this is more than 3, which means that like it has to have like it has to be 6 times like another number, and then this number has one other prime factor. So like yeah, that's just like another way you can do it, because like I saw that someone mentioned this, but like you don't I just explained that really quickly because I think the other one is like more easy to understand, and this one like you don't really have to like, it's okay if you don't understand this one. So yeah. Yes. Say yes if it made sense. I feel like there won't be as many yeses this time, but yeah. Okay, wait, that's surprising. I didn't expect this many yeses. Okay. Okay, back to Hao Tian now.
Okay, that was a very informative presentation by Jay Zhao. And we will now move on to the next and final part of this presentation. So the fundamental theorem of arithmetic. The name is pretty cool. It has adjective in the name, which is very rare. It's not that it's not it is kind of important actually. Yeah, it's very important. So a prime factorization of a number is breaking the number down into the product of the prime numbers that divide into it. So for example, I'll change to, yep. the prime factorization of 6 is 2 times 3. And the prime factorization of 12 is equal to 2 times 2 times 3, which is also 2 squared times 3. And now for some quick exercises. Prime factorize the 15, 30, 60, and P, where P is a prime. Those are your 4 problems. You have a minute. Okay, hopefully that's enough time for everyone. Yeah, so 15 is equal to 3 times 5, 30 is equal to 2 times 3 times 5, 60 is equal to 2 times 2 times 3 times 5, which is 2 squared times 3 times 5, and P is equal to P, because P is a prime. And for example, 5 is a prime, and the prime factorization of 5 is 5. 23 is 23. That's all. And again, for example, PQ, where P and Q are both primes. I'll give you a moment to ponder this prime factorization. For example, 6 is equal to 2 times 3, and 69 is equal to 3 times 23. So now we will move on to what the fundamental theorem of arithmetic is. It states that all positive integers, so 1, 2, 3, 4, 5, and so on, have a unique prime factorization. So there are 2 parts, right? The first part is every number has a prime factorization, and the second part is every number has a unique prime factorization, meaning there's only one. So for each number, they have their own prime factorization. Yeah, you can try prove it. I'll give you a moment, and then Jzao will kindly prove this theorem for you guys. Does everyone understand what a prime factorization is? Okay, you guys will have a minute to prove this theorem, which was the next problem. I might have changed the problem a bit. Yep, that's the new problem 1. Okay, because they're running out of time, I will get Jzao to present.
Okay. Once again, I'll share my screen. Right, and then once again, I'll graciously ask Hao Tian to read out the questions for me.
Prove that no positive integer has two different prime factorizations.
Oh, okay. So let's say we had an integer n, and then it had like a prime factorization. I'll just like two to the power of something, 3 to the power of something times 5 to the power of something, and then let's say it had like two prime factorizations that were like different, right? That means that in one of like for some prime, the power that it's like the prime is raised to is like different, right? Okay, does that make sense? I just want to make sure. Okay, say yes if that makes sense. That's good. Yeah, because like that's kind of like if so then if we can divide like let's say like we have in n we have p raised to a, and then in the other prime factorization we have p raised to b. So then if you divide let's just pick whatever is small. Let's just say a is smaller. So if we divide n by pa, then like this is gone, right? But then this becomes pb minus a, which is like some number. So then in this one, this would tell us that p doesn't divide this anymore. But then here, since there's still like a power of p here, then p does divide, like we get p doesn't divide n over pa, and also p does divide n over pa. So this is a contradiction. And that proves that there can't be two different prime factorizations for the same number. Does that make sense? Great. There are some yeses. Okay. Hao Tian, please read the second question.
Prove there are no two different integers that have the same factorization.
Oh, this one's like okay. This one's like I guess like it's pretty like intuitive. Like if two numbers had the same prime factorization, like you're just multiplying like the prime factorization is just like multiplying like a bunch of primes together, right? So if they had the exact same prime factorization, like after you do the multiplication, you just get the exact same number. But then we know that n and m are like different, so they're like not the same number. This one is just like it's kind of intuitive, and there's not really much of a proof to it. It's just like, yeah, but it is like it is good to know. Yeah. Okay, now Hao Tian, can you read the third question?
Oh, this question is actually left as a bonus problem to the audience.
Oh, that's very exciting.
Yeah,
That's
yeah.
cool.
It's optional. Also, there's no reason for you to be able to do this unless if you're done maths before.
Yeah. I think if you haven't like seen this before and you can figure it out yourself, you should be very proud of yourself. But like you don't have to do it.
Yeah, I believe when yeah, I could not solve this. I know. So if you can solve it, then you're actually very cool. Yeah, okay, so that's the end of this week's lesson.